Hello everyone, my name is Helena Tham and welcome to our virtual presentation on our research paper with the topic Predicting Drug Resistance in Cancer Cell Lines Using Machine Learning Approaches. Now, let's take a look at the overview of today's presentation. We will begin with an introduction and the motivation behind our research, followed by the design methodology, including dataset preparation, model development and evaluation. Next, we will present our key outcomes and a quick software demo. Finally, we will wrap up with potential improvements and future directions. To begin, let's look at the project background. The global burden of cancer is on the rise. One major challenge in treating cancer is drug resistance, such that some cancer cells can develop resistance to specific drugs, which results in ineffective treatments and failure of therapies. In response, predicting or detecting drug resistance in cancer cell lines becomes crucial for improving treatment outcomes. By using large data sources like the GDSC, CCLE, and PubChem, we can better understand the relationship between gene expression profiles and drug resistance. Machine learning therefore offers a powerful way to predict cancer cell resistance to drugs, enabling personalized treatments and improving patient outcomes in modern oncology. The motivation for this study stems from key challenges in existing models. First, traditional machine learning methods struggle with high-dimensional data, leading to increased computational complexity and overfitting. To address this, we employ feature selection, regularization, and deep learning to manage high-dimensional datasets efficiently. Next, class imbalance and data heterogeneity pose significant issues. Dominance of certain classes like drug-resistant cases skews performance while variations in data reduce generalizability. We tackle this by integrating diverse datasets, focusing on specific cancer types like breast cancer, and leveraging a pan-genome framework for better accuracy. Lastly, many models lack robustness and interpretability. By using deep learning, we enhance predictive accuracy and develop a model that is both robust and interpretable, aiding medical professionals in analysis and decision making. Here is the design of our training dataset. It includes gene expressions for cell lines, drug resistance represented by LNIC50, and chemical compound structures converted into 256-bit Morgan fingerprints. It integrates data from three key sources. First, the CCLE gene expression dataset provides profiles for different genes across a wide array of cancer cell lines representing different diseases. Using the 22q2 version, we use this dataset to capture unique molecular profiles of diverse cancers. By combining CCLE gene data with drug response information, such as from the GDSC database, we create drug cell pair datasets that enhance predictive accuracy. The GDSC2 dataset contributes drug response data, linking genetic profiles to drug sensitivity through the cosmic ID. A central metric in our project is LNIC50, the natural logarithm of the drug concentration needed for 50% cancer cell growth inhibition. Lower LNIC50 values indicate higher drug sensitivity. Lastly, the PubChem database provides chemical structure data for drug compounds. We use isosmales notation, which encodes precise molecular structures, including stereochemistry. These isosmales are converted into Morgan fingerprints, which are binary vectors representing chemical structures. Integrating these fingerprints with GDSC and CCLE datasets enables predictive models that account for both genetic data and drug chemistry, using unique 256-bit Morgan fingerprints for better accuracy. Therefore, our data pre-processing process involves three phases. In phase 1, we pre-process the CCLE gene expression dataset, extracting essential features like cosmic ID, depth map ID, CCLE name, primary disease, and gene expression. Gene expressions were used for training, while cosmic and depth map IDs enabled dataset merging. The CCLE name identified cosmic IDs and primary disease data isolated breast cancer specific entries. We rename columns for consistency, remove unnecessary features to minimize overfitting, and clean rows with missing values. The result was a clean breast cancer specific gene expression dataset. Phase 2 focused on the GDSC drug response dataset. Key features extracted included drug ID, cosmic ID, drug name, and LNIC50, which is the target feature for model training. Drug and cosmic IDs facilitated merging with the CCLE dataset. Unnecessary columns were removed and data was cleaned to ensure consistency. This resulted in a merged gene drug dataset. In the final phase, we pre-processed the PubChem dataset. Drug IDs from the gene drug dataset were exported to collect isosmouse data, focusing on GDSC2. Extracted features included drug ID, PubChem ID, and isosmouse, which were converted into binary Morgan fingerprints for training. Data was cleaned, columns renamed, and duplicates removed. Merging this with the gene drug dataset previously created the final gene drug chem dataset, integrating gene expressions, drug responses, and chemical structures. Now, let's dive into the model development and training process. Our X features include gene expression data and the Morgan fingerprints representing drug chemical structures, while the Y feature is L and IC50. We split the dataset into 90% training and 10% testing data, with the training data further divided into 90% training and 10% validation. This ensures the model generalizes well to new data. To prevent bias, we normalize the X features by removing the mean and scaling to unit variance, ensuring all features contribute equally. Next, we move to model building, where we design and compile the model architecture using the pre-processed dataset. We initially tested support vector regression and deep neural networks. DNN outperformed SVR due to its ability to handle high-dimensional data, capturing both high and low-level features effectively. The DNN architecture started with two hidden layers, which are 64 neurons in the first layer and 128 in the second, both using ReLU activation. We use the Adam optimizer for adaptive learning and mean squared error as the loss function for regression. To prevent overfitting, we implemented early stopping, halting training when validation performance ceased improving. Based on initial results, we conducted hyperparameter tuning, experimenting with neuron configurations, activation functions, epochs, and batch sizes to optimize performance. For feature selection, we explored variance thresholding, PCA, and information gain to reduce complexity and improve interpretability. However, our baseline model, which retained all gene expression features, performed best with an RMSE of 0.734, surpassing feature selection methods. This result showed that our current gene expression data inherently captured critical relationships, and feature extraction led to the risk of losing vital information. Despite the high dimensionality, we retained all features to ensure the model accurately captured complex interactions between gene expressions and drug responses. Here is the final architecture of our DNN model. Let's now look at the evaluation phase of our model. The RMSE measures the average deviation between predicted and actual LNIC50 values. With an RMSE of 0.73, our model's prediction typically deviate by just 0.73 units from the true values, which is a solid result considering the complexity of drug resistance prediction. We have met our goal of achieving RMSE below 1. The mean absolute error quantifies the average prediction error, irrespective of direction. Our model achieved an MAE of 0.52, indicating that on average, the prediction error is only 0.52 units. The Pearson correlation coefficient of 0.96 shows a very strong positive correlation between the predicted and actual values, demonstrating that the model accurately captures the data trends. Finally, the R-squared value of 0.92 means our model explains over 91% of the variance in drug resistance, indicating strong predictive power and generalizability. Overall, these metrics highlight our model's effectiveness, precision, and ability to generalize well to new data, confirming its validity. To validate our results, we benchmark our model against new PD. While both use similar drug settings, our model focused on breast cancer cell lines, integrated the GDSC and CCLE datasets, and used GDSC2, while new PD used GTSC1 and separate models. Our DNN outperformed the baseline SVR model, showing better accuracy. Compared to new PD, our model performed slightly worse, likely due to dataset differences, but still delivered valid and competitive predictions, especially in the second setting. We also compare our model's performance with other existing models. These benchmarks confirm that our DNN model is effective and reliable for drug sensitivity prediction. To evaluate our model's predictive capability, we tested it on a random dataset of 288 rows and predicted LNIC50 values. Using a resistance cutoff of 3.77, we classified drug as sensitive or resistant. The confusion matrix revealed 126 true positives, 111 true negatives, 32 false positives, and 19 false negatives, showing the model's ability to distinguish drug resistance levels while also highlighting areas for improvement. The model achieved an accuracy of 0.82. Position values were 0.8 for low resistance predictions and 0.85 for high resistance prediction, reflecting consistency in identifying drugs correctly. For example, 80% of drugs predicted as sensitive were truly sensitive, while 85% of resistant drugs were correctly classified. Overall, these results validate the model's effectiveness in predicting drug sensitivity, though there is room for refinement. Addressing the challenge of model interpretability, we developed a simple interface for drug resistance prediction by integrating our predictive model into the web application. Here is a simple demo for our software named DrugRes. The interface allows users to upload a dataset containing drug names, IDs, cosmic IDs, cell line names, gene expressions, and isosmiles. Once uploaded, the model pre-processes the data and feeds it into our pre-trained predictive model. After uploading the dataset, users can click Make Prediction, which triggers the model to run and display results in a clear tabular format. Given the cutoff for IC50 is 43.26 millimole per liter, and for LNIC50 it is 3.77, we know that predicted LNIC50 value indicates drug resistance, where lower values suggest higher drug sensitivity. Drugs with an IC50 value smaller than 3.77 are considered sensitive, while those greater than 3.77 are resistant. Additionally, a visualization of the results is provided, with the drugs sorted by LNIC50 from low to high resistance. The color coding helps interpret the results, where orange for low resistance and gray for high resistance. The interface also includes a filter to explore different cancer cell lines, assisting in treatment decision-making by identifying the most effective drugs. To conclude, here are some potential improvements and future directions for our project. First, while our model is tailored to breast cancer, expanding to multiple cancer types is essential. This can be achieved by creating separate models tailored to each cancer type. This ensures targeted predictions for each cancer type while addressing data variability and heterogeneity by focusing on similar characteristics within each model. We also need to address the dataset imbalance, where drug-related features are underrepresented. Adding more drug characteristics like molecular weight and hydrogen bonding from sources like PubChem could improve accuracy by balancing the importance of drug and cell line features. Another important area is feature selection. Currently, our model uses a large array of gene expression features, which can lead to overfitting and reduce interpretability. By identifying the most relevant features before training, we can streamline the model, reduce noise, and improve efficiency. We also see great potential in implementing an ensemble methodology. This involves combining multiple models specialized for a specific cancer type to create a unified, robust prediction system. By aggregating predictions from these specialized models, we can leverage their strengths, compensate for weaknesses, and improve both accuracy and generalizability. This framework is inherently scalable, allowing for seamless integration of additional models as new cancer types and data are added. While our model performs well, further refinements are needed for clinical use. Regular retraining, advanced feature engineering, and tuning can help achieve an RMSE below 0.5 and accuracy above 95%. Finally, our model shows great potential for personalized cancer treatment. Future work should integrate more data sources, reduce misclassifications, and validate predictions with clinical outcomes, ensuring its utility in precision oncology. That's all for our presentation. Thank you.